Alright guys, this is Pre-Calculus 2.1.2. So we're going to do a little bit of an exploratory lesson here today. And we're going to start by just kind of sorting out these. Oops, let me get back on there for you. Alright, so we have some parent functions here. Now normally we do this with like cards and use the graphing calculator and try and sort these out. I'm going to be referencing these here. So we have our linear x, our quadratic x to the second, our cubic x to the third, our exponential 2 to the x, our rational 1 over x, our absolute value of x, and then our square root, and then our cube root functions. So those are kind of 8 of the parent functions you should know fairly well at this point. So we're going to go ahead and try and examine and group these, keeping in mind that we want to look at both how they are now and then find the f of negative x of that function, so make the x part negative, and then negative f of x, so put a negative on the outside of it. Okay, and see, hey, what's that going to look like? So I'm going to go ahead and use this on Desmos to kind of help show what's going on here. So I have it set up so that whatever function I put in here for f, it'll draw a second function defined as g, as being the negative of f of x, and then our third function k as being f of negative x. Okay, so our first function is x. So I get these graphs here. So I'm going to hide these just so I can see it a little bit nicer. So there's my base graph. Okay, if I put a negative in front of it, it looks like that. I get that green graph. Right? If I put a negative on the inside, I get that. Okay, which kind of makes sense, right? Because if I have y equals x, if I put a negative in front of the whole thing, it's that. If I put a negative in front of just the x, it's the exact same thing. So what I'm seeing there is that my green and my purple are giving me the exact same graph. So that's an important distinction. Keep that in mind for how we're going to group these in the future. Okay, so now my next graph that I want to do is x to the second. So I get this. Okay, so if I put a negative on the outside, I get this green graph. If I put a negative on the inside, I get this purple graph. So that purple graph is really the exact same as my original graph is. So that's a key distinction there, right? So on that pairing, my blue and my purple were the same. Okay, so we're going to keep that in mind again for what we're going to do in the future. So then, what was the other one? Cube? Yep, cube next. Okay, so if I make this a cube, now let's see what happens here. So if I do this one, okay, so now I get this graph, and then if I do this one, I get the same thing. So now once again, my green and my purple give me the same graph. So that's saying to me, hey, I'm going to put my x to the third in the same group as my just plain old x. So my cubics and my linear, those go in the same group. Okay. Next one that we want to do is the exponential. So that's 2 raised to the x power. Okay, so here I put a negative on the front of it. It would look like that. Okay, if I put a negative on the inside, looks like that. Okay, so here none of my 3 graphs end up looking the same, right? If I put a negative in front, I get this. Negative on the inside, I get this. And original A looks like that. So none of those match. That's my first one where nothing matches. That'll be my third category thus far. Okay. So the next one we're going to do is the rational. So that's 1 over x. We get this graph. Okay. So then if I put a negative in the front of it, which is negative 1 over x, I get this. And if I put a negative in front of just the x, which is 1 over negative x, it's the same thing, which kind of makes sense again because algebraically, if I do y equals 1 over x, if I put a negative in front of the whole thing, it's equivalent mathematically to me putting a negative just in front of the x, right? So that should make logical sense to us that, hey, once again, the green and the purple were the same. So that's going to be in the same category as the linear and the cubic, right? So we have three things in that category. We have one, which is the parabola in that second category, where my blue and my purple matched up. And then I have one in the kind of nothing works category, and that was my exponential thus far. Okay, next one we have is the absolute value. The shorthand for that on Desmos is just ABS, and then parenthesis x. It doesn't change the formatting on this, but it is the absolute value of x. So there's my base graph. If I put a negative in front of the whole thing, I get flipped over vertically, which makes sense. Okay, and then if I put a negative on the inside, it's hard to see, but I get the same thing as the blue. So hey, now we're back to matching there, right? Here my blue and my purple match up, which is just like the parabola did, right? So now I can put this in the same group as my x to the second, where my blue and my purple matched up here. Okay. Next one that we're going to take a look at is the square root of x. I already have them graphed, so spoilers there, but hey, none of these are matching up, right? I got my blue, my green, my purple, nothing matches, so this is going to be added to that same category as the exponential, where none of those three are equivalent graphs. And then the final one we're going to do is x is the cubed root of x. Now there is, I believe, a button for the cubed root. If you go into like functions, thing miscellaneous, yeah, you can do it here, where that's the cubed root of x, right? The shorthand way of doing it is just do x raised to the 1/3 power, but I wanted to kind of show you that option there as well. So cubed root of x, well, I'm seeing those. I'm not seeing my green graph. That's because it's underneath my purple graph. So here my green and my purple are, again, the exact same thing. So this is going to join the same category as x and 1 over x and x to the third. So all of those are in that category, and then I have the ones where just the original matched with the purple, and then I had ones where nothing matched, right? So those are the three categories which I've gotten thus far. So what we want to take a look at now is all of these. So we got A through I, right? We're not going to do all of these by any means. I want you to pick three of them, do three of them, and see which category those would match up in. So go ahead and open up your own tab of Desmos, pick three of those 12, see what categories you would put it in. Do the A original and negative on the inside match, do the negative on the inside and the negative on the outside match, or does nothing match. Those are the three kind of categories we have come up with thus far. So try those out, see what you get for yours. Okay, so hopefully you've put those in one of those categories. So what we're going to take a look at now is how we can formally define those categories. So there we go. Okay, so we have what's called an odd function, what's called an even function, and then neither, because it could be neither even nor odd. So I don't want you to get too hung up on why they're called odd or even. There's a reason that you might kind of figure out as you kind of work with the melee bit. The reason why I don't lead with that is because that is not a rule that is the only thing which would make a thing odd or the only thing which would make a thing even. So don't stress out too much about those particular names. So whenever we had the case that our negative on the inside was the same negative on the inside same as the negative on the outside, those are called odd functions. So that was x to the third, 1 over x, and the cubed root of x. Right? All of those are classified as odd functions. Now the even functions, that was x to the second and the absolute value of x. So we got two of those in that category, and then we had those other two that were neither even nor odd. So let's think about kind of why this is happening, kind of why this works. Okay, so if we hop back over to Desmos, let's think about what these transformations mean. Okay, I'll do x to the third. It's a little bit easier to kind of see here. So when I put a negative in front of x to the third, what that's doing is it's causing me to have a vertical flip, right? It's flipping my graph vertically. So my blue graph, if I vertically flip that blue graph, you see that I would get that green graph, right? That makes sense. If I take it and I just go flip, I get the green graph. Okay. So a negative on the inside here, what that means is I flip it horizontally, right? So I flip it over the y-axis now. So if I take that blue graph, I flip it over the y-axis, what's it going to look like? That. Well, that is the exact same thing as this, right? So what this is really saying is, for this blue graph here, if I do a vertical flip, or if I do a horizontal flip, I get the exact same result. Now that's true for every single one of these quote-unquote odd functions. So let's take a look at the other ones. How about just x? If I flip this vertically, what would it look like? Well, if I flip it horizontally, what would it look like? You get the exact same thing. And you can see that algebraically too. Putting a negative in front of the whole thing or in front of the x is effectively the exact same thing, as we kind of mentioned. If I have it for x to the third, if I put a negative in front of just the x, a negative to the third power is negative overall. Or if I put a negative in front of the entire thing, so once I've done the third power, I then make it negative, I get the same result. So that's kind of why these all work. Same thing with the cubed root. All right, so if I raise it to the 1/3 power, right, same as a cubed root there. If I flip it vertically or horizontally, I get the exact same result. Likewise, if I put a negative on the inside or on the outside, I'm still going to get that negative result, which is going to work for any one of those. So, and then as I mentioned with the rational 1 over x, putting the negative in front of the whole fraction or just the x, you get the same overall result. So hopefully those are kind of making sense for us, right? That's why we have these odd functions, because this, which causes the vertical flip, and this, which causes the horizontal flip, give you the exact same result. Now, how do we define an even function? Now, an even function is when f of negative x is the same as f of x. So, hey, this is when I do a horizontal flip, and this is just the original, meaning, hey, a horizontal flip is the same as doing nothing at all. Oops, wrong screen. There we go. So ones that did that for us were stuff like x to the second, right? So if I take this blue graph, if I flip it over the y-axis, that's a horizontal flip, I get the exact same graph because it's symmetrical over that y-axis, right? So if I do this, it's the exact same thing when I flip it over that y-axis, right? That was also true for the absolute value function, right? If I flip that graph over the y-axis, it becomes itself. So it stays, right? So that's going to be an even function. So even functions are always symmetric over that y-axis, right? Meaning if I flip it over the y-axis, it doesn't change the graph at all. An odd function, doing a horizontal flip or a vertical flip, horizontal or vertical, it gives you the exact same result. And if neither of those things are true, then it's neither. So let's take a look at some of those ones you just went over. Right, so if I go back a page here. So if we graph like the first one here, x minus 1 to the second power. Okay, so let's graph that. So we'll do just a graph of x minus 1 to the second power. Okay, so let's just take a look at that graph. Okay, well, if I were to flip it over the x-axis, it would be kind of down here, right? If I flip it over the y-axis, it's going to be over here. So it's definitely not the same, so it's not going to be odd for us. Well, is it even? Because the last parabola was even too, right? Well, if I do that, if I flip this over the y-axis, I'm actually over here. I would get a graph that looks like that, right? I would get that green graph when I do that flip over the y-axis. That is different than my original, so it's not even, nor is it odd. So it's going to be neither in that particular case. Now if we hop back over here, what if we were to do like dx to the fifth plus 1? Well, this has that same kind of shape as we've seen earlier. If I do a vertical flip here, I'm going to be kind of crossing down here and looking like that. If I do a horizontal flip, I'm going to be there. So really, that one is not going to work either, right? And I can actually go back up here. Did I get rid of my f? Here, f. X equals x to the fifth plus 1. Then if I turn on these graphs, we're seeing, hey, those are different, right? That probably shouldn't also be purple. Make it back to being blue. There we go. Okay, so that one's not going to work. Well, what if I try, it's going to be a different one. Yeah, we'll do x to the sixth minus 1. Let's try this one. Okay, so on this one, if I visually do a vertical flip, I'm going to be there. Okay, and that's different than a horizontal flip, right? Vertical and horizontal are different. That's going to be not odd, and that one you should be able to kind of see pretty easily from just looking at B for actually doing those flips. Now, what if I were to flip it over the y-axis, right? Well, I would get the exact same graph, right? That's going to give me the same graph. So this one is going to be even, right? So it was weird that like when I was x to the fifth, it was neither. Oop, that was weird. To the fifth, it's neither on that. But when it was to the sixth, it was even. Okay, so this is why I don't like saying, hey, well, if I see odd numbers, it's probably odd, and if I see even numbers, it's probably even. Because that's not always going to be the case. There's a little bit more nuance to it than that. So you really want to look at those flips. Graphically, it's going to be way easier to say, hey, is it odd, even, or neither than just looking at the actual equation. So whenever you are asked, hey, is this odd or is it this even, first thing you want to do is go and graph it, because that'll make it drastically easier for you to figure out. Did I have it on the wrong scene the entire time? I think I did. Okay, so I have x to the fifth, okay, it is not, it's neither. If it's x to the sixth minus 1, it's going to be even. Hopefully we're seeing that. Sorry if I didn't have the actual screen being shown there. Okay. All right, let's hop back over here and let's wrap this up. So we've gone over those definitions. Again, trying to have those graphs is really going to help you to get the to determine odd, even versus neither. That's always my go-to when you're trying to figure that out. Okay, a little bit of notes here. This is over increasing and decreasing minimums and maximums and concavity. You went over that more in depth last time. This is kind of the more technical definitions here. This one can be a little bit unruly. I would say read through it, but don't take this down as notes at all. It's going to go over a lot more of the kind of technical definition stuff here. If the last video 211 made sense, then you're good, right? Don't worry or stress out about this more wordy definition stuff making sense to you. But do give it a read to kind of see if you can pull some stuff out of that. Okay. So again, to define even, odd, or neither. If it's even, then the original graph is the same thing as if I flip it over the y-axis. So it is symmetrical over that y-axis. If it's odd, me doing a vertical flip is the exact same result as me doing a horizontal flip. And then neither is going to be neither even nor odd. So test even, test odd, and then if it's neither of those, then it's neither. Okay. Again, graphically, it's drastically easier. There is algebraic ways to test those, but they're way more complex than we want to work with here. So we're just going to stick with the graphical way to visualize and determine those. Okay, so with that, here is our homework 22 through 29, and I will talk to you guys next time.